Hello there. In this video, we're going to do another example of how to construct confidence intervals for the population mean, and we're going to spend a little bit more time talking about exactly what this represents. So let's assume that you gather a sample of people and you calculate their systolic blood pressure. And let us assume that this sample has characteristics that the sample mean is 121.26 and the standard deviation is 1.27 millimeters of mercury. So let us assume that we know that the standard deviation is 1.13 mmHg, and let us assume we're interested in constructing an 85% confidence interval for the mean blood pressure. All right, so the first thing that you definitely need to realize is that we do know sigma for this population. If you do not know sigma, then you have to approach this problem in a slightly different way, but we'll work on a couple examples on that in the upcoming videos. But let's assume that we know sigma in this case. So if this is true, then what do we know? So if the level of confidence is equal to 0.85, so 0.85, this implies that the level of statistical significance is going to be 0.15. So if we draw a picture of pretty much what we're going to look for, we're going to develop a confidence interval, and let's assume we're going to develop a symmetric one around the mean, and we want this area right here to be equal to 0.85. So if that is the case, then that means this area right here is going to be equal to half of 0.15, and the other half is going to be on the left-hand tail. So there's going to be corresponding z values. So this is going to be the standard normal distribution, and this is the z-axis. So there's going to be z values that are going to make this area true. And we're going to call that z of alpha over 2 and minus z of alpha over 2. And these are what we call the critical values. So let's find out what critical values correspond to a symmetric 85% confidence interval. So if that is true, then that means the integral from minus z alpha over 2 to z alpha over 2 under the standard normal distribution, we want this to be equal to 0.85. And if you approach this problem as we have in the past, then you're going to find out that the critical value is going to be approximately equal to 1.4395. So this is going to be the z critical value for an 85% confidence interval. All right, so from here, what do we do? So now I'm going to calculate the marginal error for my confidence interval. So recall that the marginal error for a confidence interval, if you know sigma, is going to be equal to the critical value times the standard deviation of the population divided by the square root of n. And also remember that this is the same thing as writing z alpha over 2 times the standard error of the sample mean. All right, so what do we know? So we already know the critical value here. So that means the marginal error is going to be equal to 1.4395 times the standard deviation of the population, which was given to be 1.13, divided by the square root of the sample size. So what is the sample size? Did I state what it was? No. So let's assume that the sample size was something like 123 or something. So something relatively large. All right, so if we assume that to be true, then what are we going to get? So the marginal error for that is going to be approximately equal to 0.147. And this is still measured in millimeters of mercury. So the marginal error is going to be in the same units as what you're trying to understand. So this is pretty small of a marginal error, which is good or could be bad. It depends on how you look at this. So what does that mean? So the confidence interval, the 98% confidence interval for the systolic blood pressure, SBP, is going to be equal to the sample mean minus the marginal error, comma, the sample mean plus the marginal error. So this is going to be my 98% confidence interval for mu SBP. So that's going to be equal to the sample mean, which was given to be 121.26 minus 0.147, comma 121.26 plus 0.147, and this is going to be in millimeters of mercury. So this is going to be equal to, once you do that out, this is going to be 118.54, comma 123.98 mmHg. And again, this is my 98% confidence interval for the systolic blood pressure mean for the population. So this is what we're sort of going for here. All right, so what does this mean? So conclusion, based on my sample S, I am 85% confident that the systolic blood pressure mean lies somewhere in between 118.54 and 123.98 millimeters of mercury. So that is my conclusion. So what does this statement not mean? This does not imply that mu is in between here. So even if we were 100% confident that mu is in here, it does not necessarily mean that it is actually in there. So this is the first thing that it does not imply. It also does not imply that the probability that mu is in between these two numbers, 118.54 and 123.98. It does not imply that this is equal to 0.85, because if that was the case, then I could have chosen another number here, and technically this probability could be anything. So these are the two things that it does not apply, and this is the interpretation of what a confidence interval is. So if I have pretty much a big sample, and recall my sample size was assumed to be 123, that's fairly large, but also depends on the population. It assumes that if the sample was random, dependent, independent, it depends on quite a lot of things. But the mean could be in this interval. We do not know. But this gives us some basis for estimations for the population mean. So what else can we say? So let's take a step back and look at a couple other things in a different context. Namely, this alpha is equal to 15%. So this is pretty much a room for error. So this is a room for error, and typically sometimes people call this a type 1 error. So what is a type 1 error? Let's briefly discuss that before we get into the whole entire realm of hypothesis testing. So I have a confidence interval for the population mean, and that confidence interval came out to 118.54 and 123.98. So let us assume the null hypothesis that somebody says, let us assume that they said the mu systolic blood pressure was actually equal to 125. So if that is the case, if somebody claims that the mean blood pressure is 125, well, we already calculated a confidence interval and we're 98% confident that mu is going to be in here. So notice that this null hypothesis does not belong to this confidence interval. So if that is the case, then what could we say? So we can be 98% confident that the null hypothesis is false. So if the null hypothesis is false, then that means what? Then that means we're going to reject the null hypothesis. That the mu systolic blood pressure is equal to 125. And keep in mind, we're rejecting that under an 85% level of confidence. So that is one thing. Or let's assume that somebody else says that the null hypothesis that the mean systolic blood pressure is going to be equal to, say, 121 mmHg. So what does that mean? Well, this value belongs to our confidence interval. So we cannot necessarily reject. So we cannot reject the null hypothesis under our test. So if we cannot reject, and sometimes people call this a fail to reject conclusion, what does this mean? This does not mean accept. Just because you cannot reject the null hypothesis is not the same thing as accepting it. Because just because you cannot reject it, it could still be false. Maybe your sample wasn't good. Maybe your sample was biased or skewed or something like that. So these two types of conclusions are not the same. I've seen some textbooks and some teachers say that they are, but they are completely not the same. And just because you reject the null hypothesis does not imply that they are wrong. So let's just quickly important things. So the first important thing is rejecting the null hypothesis does not imply that the null hypothesis is false, and failing to reject the null hypothesis does not imply that the null hypothesis is true, which is why failing to reject the null hypothesis does not necessarily mean accepting the null hypothesis. So it is definitely important that you keep these things in mind. So of course this alpha, this is what we call a type 1 error. This is also known as the probability of rejecting the null hypothesis if the null hypothesis is true. And we always assume it to be true in the beginning, and then we reject it. It's almost like a innocent until proven guilty type of thing. And keep in mind, it's impossible to know. So how to know that H0 for some claimed mu is false. So the only way that you can know that the null hypothesis is false is if you know what mu is. Even if your confidence interval says that you're 99.9% confident that mu is something else and this null hypothesis is not in there, it does not mean that you know what mu is. You just have some confidence interval that is used for estimations. But this is the only way that you can know if the null hypothesis is false. That is, if you know what mu actually is equal to. So these are just some important things that you definitely need to take note of, especially when you go to the point where you have to interpret this confidence interval and make conclusions of this confidence interval that you have constructed. And it's very easy to abuse some of these conclusions, which is why it's important to take note of them here before we move forward. Because if you make any serious conclusions based on a confidence interval, you may end up committing a more serious error, which is called a type 2 error, which is pretty much, failing to reject the null hypothesis when the null hypothesis is false, which is called the beta error, or sometimes the type 2 error. But we'll get to that in a minute, or in the next upcoming videos. But these are just some important concepts about confidence intervals that you should take note of.